Amid the harsh deserts of the Middle East, where there's nothing but rocks, wind, and burning sun, the people of Israel achieved something that stunned the world. They carved more than 12,000 kilometers of canals through the desert to create a massive artificial river, channeling billions of liters of water from the Mediterranean Sea to sustain an arid nation. But Israel took it even further. They turned all that seawater into fresh, drinkable water using cutting-edge technology inside massive desalination plants. Curious how this almost unreal process actually works? Join Mandarin Tech as we dive into the story behind one of the most extraordinary engineering feats of our time. For decades, the Negev Desert in southern Israel was practically a dead land. Dry, cracked, and almost impossible to cultivate. Summer temperatures soared above 110 degrees Fahrenheit. Rain fell only for a few weeks each year, and underground aquifers slowly dried up with every generation. Agriculture, the lifeline of this young nation, stood on the brink of collapse, while many families survived on water hauled in by trucks from faraway regions. Amid this unforgiving landscape, just a few dozen miles away, lay the Mediterranean Sea, vast, endless, and filled with salt water. That contrast sparked Israel's boldest gamble, to pull the sea inland, deep into the heart of the desert. The Desert Water Project was officially approved in 2000, with an investment of nearly $3 billion. With that level of commitment and vision, Israel didn't just turn seawater into life. It challenged the desert itself, forcing rivers to flow through the sand. Before a single drop of water could be channeled, the first task was to turn the hard, barren desert into a workable construction site. They began with high-resolution satellite imagery, ground-penetrating radar, and thousands of wind measurements to map the shifting dunes and identify areas stable enough for construction. Survey teams lived in the heart of the Negev Desert for months, drilling hundreds of boreholes, some more than 100 feet deep, to study the geological layers hidden beneath the sand. Every route marker was placed by hand and recorded with centimeter-level accuracy. The entire canal alignment had to avoid the wind corridors, where a single sandstorm could bury the whole worksite overnight. Hundreds of bulldozers were deployed to flatten the dunes, cutting down the high ridges and redistributing the sand into lower areas. The goal was to create a smooth, balanced surface strong enough to support construction machinery without the risk of collapse. Each section was carefully scraped and leveled under strict supervision, with surveyors checking elevation and slope to ensure uniformity across miles of open desert. Conveyor systems pushed the excess sand away from the work zone, while compactors gently pressed the top layer to form a firm and workable foundation. After the bulldozers had leveled the dunes, the sand still needed to be stabilized. Engineers discovered that injecting water into the loose surface helped bind the grains together, creating a denser and more cohesive layer. Using long sprinkler arms and underground pipes, they sprayed controlled amounts of groundwater across the site, allowing moisture to penetrate several inches deep. Once the sand reached the right level of dampness, heavy rollers moved in, compacting the surface to remove air pockets and lock the particles in place. The constant rumble of steel drums echoed across the desert as each pass of the roller turned soft, shifting sand into a firm, uniform base. By the time the surface dried under the desert sun, it had hardened enough to carry the weight of cranes, mixers, and supply trucks. A solid foundation built from nothing but sand and water. Once the groundwork was complete, hundreds of excavators and massive dump trucks began one of the largest digging operations ever undertaken in modern Israel. Every day, around 70,000 tons of sand and soil were removed from the Negev Desert, along a construction corridor stretching nearly 250 miles. Over 1,200 engineers, operators, and laborers worked in rotating shifts, enduring daytime temperatures that often exceeded 115 degrees Fahrenheit. The canal was shaped with a wide U-profile, about 150 feet across at the base and an average depth of 23 feet. To allow water to flow naturally without pumps, the longitudinal slope was held within 1 inch per 100 feet, an incredibly tight margin over such distance. Survey crews rechecked elevation with laser leveling instruments every 160 feet to ensure the canal floor stayed perfectly aligned. Most of the excavated sand was reused to build up both sides of the embankments, forming levees 10 to 16 feet high. In hilly terrain, bulldozers cut the layers step by step, while in low-lying areas, trucks hauled and stabilized fill material until the grade was reached. In weak soil zones, engineers drilled 16-inch sand piles up to 20-25 feet deep, or mixed cement and clay to strengthen the base and prevent subsidence. The construction site stretched for hundreds of miles, dotted with concrete batching plants, mechanical workshops, and field engineer camps. Under the scorching sun and swirling dust, long convoys of trucks and machines moved endlessly, a mechanical river carving the shape of a real one into the heart of the Negev desert. This excavation phase lasted for months. In the Negev desert, the challenge wasn't just the heat and dryness, it was the thirst of the sand itself, capable of absorbing any exposed water within hours if the canal bed wasn't properly sealed. That's why the lining phase became one of the most critical stages of the entire project. First, the canal bed and slopes were moistened and leveled with a 2-inch layer of fine sand. Then concrete panels about 4 to 5 inches thick were poured into sections measuring 16 feet long by 10 feet wide, each separated by expansion joints. These joints were filled with hot bitumen sealant to prevent seepage and allow thermal movement. In areas with unstable subsoil, an additional HDPE geomembrane layer was placed beneath the concrete, fixed with steel anchors and covered with a protective sand cushion. Altogether, more than 220 miles of canal were lined with concrete, making it one of the largest waterproofing systems ever built in the Middle East. Along the embankments, engineers planted vetiver grass and desert acacia to stabilize the slopes and minimize sand drift. From above, the canal appears like a shimmering silver ribbon cutting across a sea of gold, a concrete artery waiting to carry its first life-giving water through the desert. A massive canal can't simply be a trench for water. It requires hundreds of auxiliary structures to ensure transportation, flood control, and proper water regulation. At the head of the system, engineers from WAPDA built the head regulator at the Townsah Barrage, where water from the Indus River is diverted into the canal through 9 enormous steel gates. Along the main route, there are more than 900 different engineering components, including reinforced concrete bridges, spillways, siphons, drainage culverts, and aqueducts carrying water across natural streams. Whenever the canal intersects a road or railway, a new bridge is constructed to maintain traffic flow. In sections that cross natural waterways, cross-drainage structures are installed, large conduits that allow the natural flow to pass beneath the artificial canal. In addition, distribution gates are placed every 6 to 9 miles to control water flow into secondary branches. Everything must operate in perfect harmony because a single malfunction, whether at a gate or an aqueduct, could deprive hundreds of hectares of farmland of their water supply. After more than 15 years of construction, the entire canal finally entered the water testing phase. Engineers opened the gates at the Townsah Barrage, letting water from the Indus River flow section by section, gradually increasing the discharge from 500 to 2,000 and then 6,000 cusecs. Along the route, technical teams inspected every point, measuring pressure, checking for leaks, monitoring the canal slopes, and recording any ground movement. Every deviation was corrected before the system was fully opened. When the first rush of water flowed through the cracked, dry canal bed, the regions of Dera Bugti and Jalmagsi erupted in celebration. Locals called it the day the desert came back to life. Wherever the water reached, cheers followed. It wasn't just a flow of water, it was a flow of hope. The fulfillment of a dream generations of farmers had waited their entire lives to witness. The moment real water finally ran across their land. The water from the Mediterranean finally makes its way through the artificial river that cuts across the desert, but it can't reach people just yet because it's still seawater, and in the desert, salt can be even more dangerous than drought. Before becoming a source of life for millions, it must pass through an intelligent desalination system, a chain of advanced technologies stretching from the coast deep into the inland. Here, seawater goes through multiple stages: mechanical filtration, sand settling, oil separation, and then nanofiltration and reverse osmosis, RO, where every salt molecule is removed, leaving only pure, drinkable water. Digital sensors constantly monitor salinity, pressure, and flow, automatically adjusting the process to maintain the highest level of purity. Only after passing all these layers of control does the water enter the main canal, beginning its hundreds-mile journey across the Negev Desert. No longer seawater, but a true lifeline for an entire nation built on hope and resilience. The pretreatment stage may have already captured large debris and sediments, yet seawater still carries countless fine particles and microscopic organisms. To prevent these from clogging the heart of the technology that follows, a phase of fine filtration is introduced. Inside massive filtration tanks, black hollow fiber membranes act as ultra-thin barriers, blocking algae, bacteria, and even the tiniest remaining particles. The initial filtration stages are only the beginning. The decisive phase unfolds within the reverse osmosis system. Under immense pressure, seawater is forced through semi-permeable membranes, each pore hundreds of times smaller than a strand of hair. This invisible wall allows only pure H2O molecules to pass through, while salts, heavy metals, and trace chemicals are left behind. High-pressure pumps generate tens of bars of compression, transforming the salty, murky mix into a stream that's nearly pure. Yet as it leaves the RO modules, the water is so pure it becomes almost empty, and that very emptiness must be corrected. Precise dosing systems add small amounts of calcium and magnesium to rebalance pH and restore a clean, natural taste. Next comes disinfection. Ultraviolet light, or ozone, eliminates any remaining microorganisms, while a trace of chlorine ensures long-term safety through the pipelines. Every parameter is monitored in real time, and lab samples are analyzed constantly. Only when all standards are met is the water pumped from storage tanks into the distribution network, flowing through miles of underground pipes to homes, hospitals, and factories. It is a complete cycle where the salt of the ocean is transformed into safe, drinkable water, a testament to the remarkable power of modern technology. When the first flow of water crossed the Negev Desert, everything began to change, not just on the surface, but deep within people's lives. Land that once cracked under the burning sun started to come back to life. Farmers who had once left because of drought returned, pitching tents, driving stakes, and plowing the first fields of their lives amid the sand and rock. Water from the main channel of the national water carrier was divided through a network of secondary canals, pressure pipes, and drip irrigation systems that delivered it directly to each plant. A technology Israel itself invented to save every drop of water as precious as gold. The project began in 1953 and took over 11 years to complete, costing around 420 million Israeli lira, equal to hundreds of millions of dollars at the time. Once operational, the system could transport up to 72,000 cubic meters of water per hour, bringing fresh water from the north all the way down to the Negev. As a result, regions once thought hopeless were revived into thriving agricultural zones. In the early years, tens of thousands of acres of farmland turned green. Where there was once only dust and sun, now stood orchards of oranges, vineyards, wheat fields, vegetable farms, and rows of date palms heavy with fruit. Seen from satellites, a long green ribbon winds across the Golden Desert. The green artery of Israel, the artificial lifeline connecting the north and south of the country. The transformation went beyond the fields. Villages were rebuilt, children had schools, and high-tech farms rose from the sand. So, you have learned the whole story of how the Israelis dug billions of tons of sand out of the desert to create the longest river in the world.